All right, guys. Okay. So first off, let's start with our warm-up. So in exercises 1 and 2, find the scale factor of the dilation, then tell whether the dilation is a reduction or an enlargement. All right. So first, remember K, which is our scale factor, is always going to be equal to CP prime over CP. So in this case, the distance between C and P prime is the larger one. That's going to be 27 over. And then the distance between C and P is 9. Okay? Remember, when K is greater than 1, in which case this is actually 3, then it is an enlargement. Which makes sense, okay? Because it's going to be getting bigger. Now, for the second one, we've got K equals CP prime over CP. CP prime is 4 over, and then CP is 10. Okay? So this turns into 2 over 5. Now remember, when it's less than 1, when K is less than 1, but greater than 0, it's a reduction. All right, and that's our warm-up. This is lesson 4.6. We're still in chapter 4. This is the last lesson of chapter 4. Okay, so this is chapter 4, section 6, similarity and transformations. So you guys have heard the term similar. That's when triangles or other shapes, they're exactly the same shape, just different sizes. So all of their angles are the same, but their lengths are different. Okay, so a dilation is a transformation that preserves shape but not size. So dilation is a non-rigid motion. Remember, rigid motion is when you preserve both the shape and the size. Those were the 3 transformations we learned before, like translations, reflections, rotations. Those all are rigid motion, okay? A similarity transformation is a dilation or a composition of rigid motions and dilations. Okay, so similarity transformation basically says that you're not preserving the congruence of the image, so you are changing the size of it, but the shape is staying the same, so it's a similarity transformation. 2 geometric figures are similar figures if and only if there is a similarity transformation that maps one of the figures onto the other. Similar figures have the same shape, but not necessarily the same size. Basically, if we use any of the transformations we have learned, the figures will be similar. So any of the ones, dilations, rotations, reflections, or translations, those 2 images will be similar. All right, congruence versus similarity. So we got some questions for you. What is the difference between similar figures and congruent figures? Think about this one. Okay. The difference is similar figures do not have to be the same size. Are congruent figures similar? Yes. Okay, if 2 figures are congruent, they have to be similar, okay? They have to be the same shape. Are similar figures congruent? Not necessarily. Not always. Okay? You could have 2 figures that are similar and congruent, okay? Because congruent figures are similar. But if you have 2 figures that are similar but not the same size, so they're not congruent, that is possible as well, okay? If our scale factor is 1 or -1, so K equals 1 or -1, would the dilation create congruent or similar figures? And this one is congruent. Okay? Because when K equals 1 or -1, you're not changing the shape of the image. Okay? You are just, if it's -1, you're rotating it 180 degrees. If it's positive 1, you're not changing it at all. Okay, this next one, we're going to actually perform a similarity transformation. So we're going to graph ABC with vertices A at -4, 1, B at -2, 2, and C at -2, 1. So let's go ahead and do that. A, B, and C. So A is at -4, 1. We go -1, -2, -3, -4, up 1. Here's A. B is at -2, +2. So that's right here, B. And C is at -2, +1. Here's C right here. So it's a nice, small, little triangle, okay? Its image after the similarity transformation. So first, we've got a translation. So we're shifting the image to the right 5 and then up 1. I'm just going to do that graphically. But remember, we always want to recalculate our points because we have to perform this dilation afterwards. So let's take a look. So A prime, if we add 5 to its x term, is going to be 1. And add 1 to its y term, it's going to be 2. So it's going to be at 1, 2. B prime is going to be at -2 + 5 is going to be 3, comma 3. C prime is going to be at 3, comma 2. Let's plot those. So A at 1, 2 is going to be right here. That's A prime. B prime is going to be at 3, 3 right here. And C prime is going to be at 3, 2. Perfect. That's after one transformation, okay? That's after the translation. Our second one is going to be a dilation. So we're going to take all the x and y coordinates and we're going to multiply them by 2, okay? So our scale factor is k equals 2. So A prime is going to be 2, 4. B prime is going to be 6, 6. And C prime is going to be 6, 4. When we plot these, we'll see exactly what happens, okay? So 2, 4, remember, dilations, whenever it's not specified, it's always about the origin, okay? So we can apply our coordinate rules here. Okay, 2, 4 over 2, up 4, 1, 2, 3, 4. A double prime. I put A prime, my bad. This should be double prime. B double prime is at 6, 6. So 1, 2, 3, 4, 5, 6. Up 6. So 1, 2, 3, 4, 5, 6. 6, 6 is right here. This is B double prime. And C double prime is at 6 and then positive 4. So here's C double prime. Okay. Remember, we can eyeball it, but we can also actually determine what if we dilated the right way by using the line test. So let's draw a line to A double prime, to B double prime, and to C double prime. And I noticed that all 3 of those lines pass through our original points, A prime, B prime, and C prime. So we dilated it the correct way. So this is what's called a similarity transformation, going from this image to this larger green image, okay? Similarity transformation. Even though these two triangles are not the same size, right? The green one is larger, they are still similar, okay? Because we performed only transformations and both of those maintain similarity. Okay. And our image looks just like that. So we did a good job, okay? All right, practice, you better have time for that, okay? So let's go ahead and graph CD with endpoints -2, 2, and 2, 2, and its image after a rotation and a dilation, okay? So let's go ahead and do that. I gave you guys graph paper. I'm just going to have to wing this one. All right, so let's do C is at negative 2, 2, negative 2, up 2. You're right here. This is C. And then D is at positive 2, up 2, D. So it's this line segment right here, okay? C prime and D prime. C prime and D prime. Okay? Now, remember, rotations. That one's going to come first. And if it was AB, look, our coordinate rules for a 90-degree rotation about the origin is going to be negative B, comma, A. All right? Now, so let's go ahead and apply that to C. So C's A coordinate is negative 2. That's going to move over here to the B spot. And the 2 is going to move to the A spot, but also be negative. So negative 2, negative 2. Same thing for D, okay? So D, its A coordinate is 2, so it's going to move over here. And its B coordinate is 2, so it's going to become negative 2 over there, okay? All right, now let's go ahead and plot that. So that's negative 2, negative 2. So we're going to go down 2. That's right here. This is going to be C prime. And negative 2, positive 2. This is going to be D prime. All right. And then lastly, let's do C double prime and D double prime after our dilation, okay? So our dilation is now 1/2. So it's actually going to become smaller, okay? So C double prime is going to be negative 2 times 1/2, which is going to be negative 1, negative 1. And D double prime is going to be negative 1, 1. Negative 1 is right here, and negative 1, 1 is right here. This bottom one is C double prime, and this top one is D double prime. We could always check it by doing our line test. Oops, there's a bad one. And looks good to me. They both pass through both points. All right, perfect. And looks good to me. Okay. Now, in this lesson, also you're going to be asked, or you're going to have to be required to describe a similarity transformation. So a combination of transformations that maps trapezoid PQRS to the smaller one, WXYZ. Okay? Now, for this one, I will help you out with it. So let's take a look at the blue one compared to the green one. Well, I noticed this point right here, right? Let's call it the nose of the trapezoid. It's facing the other way in the green one. So we know we're going to have a reflection. And if we reflect it over the y-axis, that would be really easy, okay? Just because that would automatically flip it. So let's first perform a reflection about y-axis, okay? So that's going to move all the points from the left side of the axis to the right. The only one that stays the same here is going to be that r. Why? Because r is on the axis. So this is going to be r prime. S is negative at -6, so it's going to be at +6. And it's going to have the same y coordinate. So this is going to be S prime. Same thing for Q. Q is at -3, 3. So its x coordinate is going to change to positive, so it's going to be a +3, 3. So this will be Q prime. And then P will be all the way over here. P prime. We connect all the primes, and we get something like this. and this should look exactly like our other trapezoid, and it does. It's just flipped, so, or reflected over that axis. All right, so we're good, okay? Now, step number two. Step number two, I noticed that we did shrink it, right? Now, let's compare R prime is the same point as Y, right? So how much are we going to have to shrink it in order to get there? Well, let's take a look at the coordinates. So R prime is at 0, comma, -3. And Y is at 0, comma, -1. So technically we divided by 3, right? If we were going to multiply something to this, we would be multiplying by 1/3. So let's try that. Let's try 1/3 for each. So R prime, let's do dilation. K equals 1/3, okay, to all of our coordinates. So if we were to take R prime at 0, -3, R double prime would be 0, comma, -1, okay, because we're dividing by 3. Let's take S prime. S prime's coordinates are at 6, -3. 6, comma, -3. So S double prime would be 2, comma, -1. Let's see where that ends up. That's over 2, down 1. That's going to be right here. That's Z. That's a good match, okay? And then let's take P prime. P prime is at 6, 3. P double prime, after you multiply both the X and the Y term by 1/3, is going to be 2, 2, comma, 1. Okay? Q prime is at 3, 3. That's right up there. So Q double prime will be at 1, 1. And those are both these 2 points. So we just used described a similarity transformation that maps our original trapezoid, which was the larger blue one, into the smaller green one. Let's see if the book did the same thing, and they did. They reflected it over the y-axis, and then they shrunk it by 1/3. Or they reduced it by 1/3. Oops. Okay, and we're going to do one more example, okay, because there's never too much practice. So describe a similarity transformation that maps quadrilateral DEFG to quadrilateral STUV. Now, whenever there is a difference in the size, right, there has to be a dilation somewhere, because none of our other transformations change the actual size of the image, right? So DEFG shrinking down, it's got to be a dilation somewhere, but let's take care of how it looks first. I noticed that this G, right, should match up with the V, and the F is kind of like the nose, and that matches up with the U over here. So it almost looks like it could be a reflection, but if you look closely, it's more like a rotation, okay? So if we rotated this image, right, if we rotated it over here, it would, if you trust me, it'll look exactly like how we need it to. Because a reflection, you see, would like still keep it upside down. And at this point, it's kind of like right side up, okay? Let's just try it. And the more you do these, the better you'll get at them. So don't be worried if you're like, I don't see it, okay? You just got to keep practicing, okay? It comes more natural to other people. So if you're not seeing it right away, you got to keep working hard, okay? Okay, so if we rotate it 180 degrees. Let's see what happens. That'll be step number 1, okay? A rotation of 180 degrees. Remember, if you have a rotation of 180 degrees, your AB is going to be negative A, negative B, okay? So let's go ahead and find all of the coordinates of our blue quadrilateral. So F is at 4, 0. G is at 0, 1. D is at -2, +3. And E is at +1, +4. Okay? Let's rotate it. So this is going to be F prime is at -4, 0. G prime is going to be at 0, -1. D prime is going to be at 2, -3. And E prime is going to be at -1, -4. When we plot this using a different color so we can see the difference, we're going to see that it does reflect a rotation about 180 degrees about the origin. So F prime is going to be right here, F prime. G prime is going to be 0, 1, or 0, -1, excuse me, G prime. D prime is at 2, -3. That's going to be right here, G, or I'm sorry, we already did G. This is D prime. And then E prime is at -1, -4, so right here, E prime. If we connect these, we should have the exact same image, just rotated. And that looks pretty darn good. Okay? All right, so now we have to dilate it, okay? And I see, all right, look. Let's take a look at G prime. Remember, G matches up with V, so it looks like it shrunk by a half, right? And also F prime and U, right? It shrunk by a half. So let's use K. Let's say K equals 1/2. Let's try it. Let's just try it. So if F prime was -4, 0, F double prime is going to be at -2, 0. G double prime is going to be at 0, -1/2. D double prime is going to be at 1, -3/2. And E double prime is going to be at -1/2, -2. Let's plot them and see if we get our green quadrilateral. So F double prime at -2, 0, that's right here. Beautiful, that's now U. G double prime is at 0, -1/2, that's right here. Good. D double prime is at 1, -3/2, which is -1 1/2. That would be right here. And T is at -1/2, -2. Right here. That exactly is our green quadrilateral, so we're good to go. Our second move was a dilation. Scale factor 1/2. This says I always like to rotate or just get my image to where it needs to be, and then I would shrink it. Dilation with a scale factor of 1/2 followed by a 180-degree rotation about the origin, okay? So if you had done the dilation first and then rotated it, it would have also been right. I visually... Okay, I added this slide just because I think this is a great coordinate plane. So when you guys are doing your homework and stuff, if you ever have like smaller graphs, this is a really nice one to use. So if you want to copy this one, you can. It's a great tool for just like setting up. You can, I believe you can like take a snippet of it and then just like have it like in your iPad somewhere to just like paste, or in your Notability. Here's your homework. Good luck, and I'll see you guys tomorrow.